Hi all, and welcome to day 23 of Advent of Elixir. Today I'm going to talk about term to binary. So term to binary is how Erlang and Elixir serializes Erlang terms and into a unified binary representation. So if you've ever used Python, it's kind of similar to Python's pickle function, but let's be clear, it is much more well designed than pickle. Term to binary will work in almost all cases in almost always the way that you expect. I will show you an example of how it might not work in the way that you expect. And since the Beam type system is so constrained, it works pretty much every Beam architecture. So if you're running two versions of Beam that are a little bit out of date from each other, most likely term to binary will still work, even if they're not running the same version. So why does this exist? I think the biggest argument for why this exists is to have a unified way to ship information from one node to another one over the network. And basically Erlang clustering would be impossible without term to binary. So with that all said, let's take a look at term to binary. So the first thing I'm going to do is I'm going to spin up a Erlang node or an Elixir node. And we're going to go ahead and just get ready to use clustering with this. And okay, so let's go ahead and use Erlang term to binary. So I'll show you what a few basic terms look like. So erlang.term to binary. And then let's look at, say, a number. Let's pick that number. And I'll quickly go ahead and explain to you how you can understand term to binary. And for some of a few more complicated examples, we're going to go a little bit deeper. So basically all binary versions of a term will begin with the byte 131. So that's a magic cookie that tells you that this indeed is a result of a term to binary. Then the second byte will tell you the type of what it is. And then there's an arbitrary amount of extra information that follows in the binary. And sometimes you can take a look at the binary and see what is in there. So for example, look at this term to binary 47. You can see this 47 very clearly hanging out right there. That's because 47 is less than 256. It fits in 1 byte. 97 is a code for an integer that fits in 1 byte. And so there you go. 131, 97, 47. You can also represent a bigger binary. For example, 256 is exactly is 1 byte. So let's go ahead and do 256 and see what it does. And you can see there's a 98, which is a slightly bigger binary. In this case, it clearly supports 4 bytes. And the 4-byte representation of 256 is 0010. So this is what that sort of a number looks like. Let's look at a string. So a string might look something like this. 109 means a binary value. And then what we see here is some number, 4 bytes, which tell you the length of the string. And in this case, the A string is 1, 2, 3, 4, 5, 6, 7, 8. So that's why you see the number 8 there. And then if you're familiar with ASCII, you'll immediately notice that 97 is the letter A. So that should give you a hint that this is actually a string. And to prove that, what I'm going to do is I'm just going to copy paste that one section, and you'll see that that is in fact a string. Let's also do an atom. So Erlang term to binary, an atom. And here you have 100, which says it's an atom. Atoms are actually constrained to being 256 bytes long, and so there's only a 2-bit signature that tells you how long it is. There are 7 characters in this atom, AN underscore ATOM, that's 7. And here again, you see 97, which is the letter A. It's a hint that this is actually encoding an atom. So let's go ahead and do that again. And you can see you get the string an atom out. So these are kind of some examples. Let me show you, for example, also a tuple. So erlang.term to binary. Let's do a tuple that has the number 47 and foo. You can already see 47, 9747, right? This is the code for an integer of 47. 104 is the code for a tuple. 2 tells you how many items are in the tuple. Then it goes to 97 and it says, okay, here I've got an integer of size 47, and then an atom, which is 100, of size 3 with 102, 111, 111, and you can pretty much guess what 102, 111, 111 is. I don't have to decode that for you. So let's also do a list. This one will be a little bit trickier to read because lists are cons cells, but maybe we can figure it out. So 108 says it's a list. And what it will do is it'll actually compress the list into a flattened list. So 108 is just a list, and here it says the list has 2 items. It's 4 bytes telling you how long it is. Again, 9747 for the number 47, 100, 03, 102, 111, 111 for the atom foo, and then 106. Why is there a third 106 right there? Well, 106 is the code for empty list. So if I show you empty list, there you go, 106. In a previous video, you may have heard me say that empty list is the smallest data type representation in Elixir. That's why, because this is just the binary code 131 plus a single byte that says, hey, this is an empty list. It's a special type of its own. Why does it have to do this? Because this makes the distinction between a 2-item list that is an improper list. So let's look at that. Here we have the improper list 108, which has 1 item that's a proper item, that's 9747, and then 100, 03, 102, 102, 111, 111, and this is the terminal item, which is just foo, whereas the terminal item for this list actually is capped with an empty list. So this is kind of how you can sort of parse these term to binaries that have been generated out of terms. I should also show you the reverse operation. So the reverse operation is erlang.binary to term. So let's go take a look at some of those. So first I'm going to decode the result from the first one. And so we see 47. Let's decode a string, which is number 3. So we see a string, right? And then let's decode an atom, which is number 5. And let's decode our tuple, which is number 7. Let's decode our list, which is number 8. And let's decode our improper list, which is number 9. Okay, cool. So you can see how all of these things. Sorry, that was empty list. Let's do our improper list, which is number 10. So you can see how it's very easy for Erlang to serialize any sort of term that you have in the system and turn it into something that's pickleable. And what do I mean by pickleable? Well, for example, let's take our number 10. So this is Erlang term to binary 47 improper list with 40. So what I'm going to do is I'm going to go ahead and save it to this file term. File.write. Okay, so we just wrote that to this file term, which you can see over here. We're going to take a look at some of those later. But I just killed my virtual machine. Now I'm going to start it up again. And then I'm going to read that file.read term. And you see we got that data back. And then now we can do erlang.binary to term. The previous value, and we see that it recovers the value even after it's been evicted from memory because I have shut down the virtual machine. So that's the essence of pickling. I can send it, I can save it, and presumably I can also send it over the wire, and another virtual machine that is either distant in time or in space can then pick that up and do something with it. Okay, so let's look at some more kind of interesting use cases for this. So the thing that I'm going to do now is I'm going to go ahead and do self. So let's go ahead and save, do binary to term on self, or excuse me, term to binary. And then what I'm going to do is I'm going to save that. To this file term. So now term contains this self PID. It's a PID. Note that the self PID is 207, and you do indeed see that 207 kind of hanging out right there. So you have a good sense that that's actually made it into the term itself. Now what I'm going to do is I'm going to spin up another virtual machine. We're going to call this one sname write cookie cook and then snix. So now on the right hand side, I also want to just inform you that I've made it so that node.list, I've made it so that these two are automatically connected. So the left-hand side is in a cluster with the right-hand side. Now I'm going to file.read the term. And then we're going to do erlang.binary to term on that value. And whoa, 207 is still there, but our first number is not 0, which is what you might expect, but it's 20276. That's really cool. What happens if I send that value a message? Hi from right. Then I can flush the message queue on this guy, and you can see that the hi from right hand side message that I sent from the right hand side is there. So what was really cool was we saved the self PID, serialized it as a term to binary, and then when it rehydrated on the right hand side, it knew exactly what was going on. So how did it do that? Well, what I'm going to do is I'm going to go ahead and I'm going to open this term file, and then that'll maybe give us a little bit of a hint as to what's going on. So with the text editor, we're going to take a look at exactly what exists in here. And here you can see there's left at pop OS is a part of the string. So encoded inside of this is actually the name of the node as an atom, so that it knows that in fact this self PID is localized to this particular node. And so long as this node is that PID is still active on this node, I can of course send messages once I rehydrate it from the binary on the right hand side. And this is exactly what is happening when you send PIDs over the Erlang cluster. It's doing a term to binary. The term to binary payload on that PID contains the node name. And that's how it's able to have consistent resolution of all these weird front prefixes on the PIDs. Okay, so that's cool. What I did was I just showed you how term to binary does PIDs. I want to show you one more thing, which is kind of cool. What we can do is we can send lambdas over. So, a lambda, a function, is just as much a term as any other term. We're in a functional programming language, so they're first-class citizens of the virtual machine. So, for example, advent.doSomething with an arity of 0 as a lambda, that's a function right there, right? So what happens if I take that value and run term to binary on it? Well, that creates some sort of binary representation. And then let's go ahead and save that. And then I'm going to kill my virtual machine. And then we're going to pick it back up. Now we're going to read it. And then we're going to do erlang binary to term. And you can see it already just knew that was advent.doSomething, right? And then what I can do is I can, of course, run it. And it does exactly what you expect, which is hello advent. Okay. What happens if I load it on this side? And then what happens if I run that again? You can see it knows it's advent.doSomething, right? And then I can execute that. And it does hello advent. Now, what I'm about to show you is one of the ways in which this kind of can get messed up. So let's go ahead and do this. We're going to kill our virtual machine, and then we're going to run it, except this time we're not going to smix it. So let's go and do this. So by not smixing it, what that means is that this virtual machine doesn't load up the existing project. So it won't know about this advent module, right? So if I do advent, I can't tab complete it. If I try advent.doSomething, it won't know what that is. So what happens now if I file.read term and then erlang.binary to term, it still thinks it's advent.doSomething, but if I try to run that, it says the module advent is not available, which is exactly what you would expect. Okay, let's do one more thing. We're going to again reload the virtual machine, but this time with the code, right? But I'm going to change it, right? And then I'm going to recompile. Now what happens when I read the file? And if I run it, I'm going to get hello changed, even though if I run it on this side, I'm going to get, I'm going to get hello advent, which is the old code. So do note that it's only understanding what's going on as a reference to the existing, to the whatever module exists in memory. So if your two nodes have different code inside of them, advent and do something are just reference markers to a specific set of names. If those names don't exist, you'll get a I don't know what this function is error. And if the two functions have different implementations that are out of whack, then they may wind up doing different things that you aren't expecting. So one more thing we should do is let's crack a look at what this term looks like by opening it in a hex editor. And here you can see elixir.advent, which is the atom for the module, and you can see do something, which is the function name. Okay, so that is kind of a deep dive into how Erlang term to function, Erlang term to binary and binary to term work. I think you can begin to understand where some of the tricky parts of Erlang clustering come from, but also why it's so easy to actually implement a good clustering system in the Beam ecosystem, where a lot of other programming languages and programming systems struggle really hard to get that right. So because Erlang and Elixir are built on top of such robust foundations, that's what allows us to do such magical things with this programming language. Okay, that was a lot. I will see you tomorrow.